Spark here again. This is going to be a different type of video, kind of. Um, I have been kind of curious obviously with quantum gravity, because we talk about this on the channel, as well as consciousness and stuff. I have done some work in doing the whole modeling of the graphical representation that I have in mind. Um, and seeing maybe there are other areas where it may apply to as well as a measure of emergence and convergence, that sort of thing. Because if it's relative to consciousness, consciousness is an emergent quality that would explain the emergent quality in and of itself, and the convergence is the collection of ideas in order to get down to the brass tacks of things, in a sense. Or convergence being how the internet, you can look at the internet as a convergence of human consciousness, and that's what kind of AI is going to end up being, and all that other stuff that we've talked about on the channel. So I've also been curious in regards to quantum gravity, because obviously it will have to do with understanding black holes. I've been looking up the different pressure density equations, as well as like measurements for neutron stars in particular, because that is a typically, besides obviously a quark star, where we get to a point where the whole gravity starts breaking down and we get to a black hole. And in order to explain the innards of a black hole, we need to understand how gravity works in regards to particles, because we can measure the type of particles that escape from a black hole, which is gamma radiation, Hawking radiation, neutrinos. Neutrinos is, like I've said before, is definitely going to be the key to a lot of this, to understanding this, because of the fact that, again, my idea is that literally space is made of neutrinos. It is just made of neutrinos. There are obviously neutrino, anti-neutrino parts, but they annihilate into, I think, two photons. And that would make sense with the whole end of the universe being just photons, and then the collapse because of, the true vacuum being realized as a false vacuum, yada yada. A bunch of other ideas that we've thrown out here. So, more that relates to trying to figure out that understanding, because if we understand again how gravity actually works in the quantum realm, we understand the expansion of space at that point, because what's made of space? Space is made of particles, it's particle fields, right? And there's also like loose atoms as well, like oxygen. Like in our atmosphere, we have oxygen, nitrogen, all these other things. In space, you have hydrogen, helium, possibly. So very low count atoms. So understanding that's how space is made up, and how gravitational waves pulse through that, with the, at least how I theorize, with the addition of other particles in the space, right? Like with black holes, for instance, the what was it, this whole idea of approaching a black hole, and you're going to the speed of light at that point, because of the rotational speed of a black hole is very close to the speed of light relative to the inertia with the singularity. Um, and then all the forces involved with rotation, and as well as alongside the pressure density mass, alongside the volume, with which this is what I'm currently trying to work through, is the factor between density and volume, because I feel like that has to do with obviously gravity alongside vacuum pressure, or vacuum pressure energy. I feel like those two things, alongside with the whole idea that we looked at before in our previous quantum gravity video in regards to thermodynamics and electromagnetism, both being a factor in calculating quantum gravity, as maybe a sum of the force effects from those, well, from the thermodynamic side, because energy turns into heat, turns into light. That is how we measure energy typically, is through heat. If something is letting off energy, or is interacting in some way, or has activity, we, you know, there's heat. That's how space works. It's the whole idea of a heat death, when the end of the universe and the whole vacuum breaks down, is that there's no energy moving anymore. There's nothing left. This is just, everything's broken down to photons. And it's going to take an immensely long time, even after we're all gone. Even after baryonic matter is all gone, it's going to take an immense amount of time for all that to pass, because of just the amount of space that will exist. Because for whatever reason, neutrinos are the one thing that just cannot recombine to anything meaningful. They just annihilate with their anti-neutrino parts if they exist, and they break into photons, or they'll just float into space. Because we use neutrinos as a way to measure the history of space, just like how we measure like carbon dioxide and ice for, how old the Earth is to a certain extent, or the how the atmosphere was at different ages of the Earth, and that has to do with the whole equation idea, etc. So this is why I'm just throwing it out. What I'm looking at now is the basically the shift where, I mean, a neutron, because that's the one particle, especially in regards to the change in state of a neutron star to a black hole. Because if we can understand at a point where neutrons are broken down, forced to be broken down due to density at that point because of gravity, and trying to understand gravity as a measure of the vacuum energy just due to proximity or the lack thereof, because I mean the closer something is, then the more vacuum pressure there's going to be, or vacuum energy there's going to be when there's two masses. That's why I think gravity might have to do with that in terms of the quantum realm. And it's going to be a summation of, I mean, obviously there's the aspect of spin, because spin versus counterspin, there's going to be a force of repulsion at that point. And then when two things are spinning in the same direction, it's going to be propulsion, I would assume, when it comes to momentum and spin and centrifugal force and all that. Because that will be a force that might be meaningful in the quantum space from particle to particle when it comes to their interactions. Because we obviously understand spin, we understand anti-spin, we understand that when there's, that collision with anti-spin, there's annihilation. That makes sense, right? As a concept. So, and with how, I mean, most of space is made of matter, things that exist, things that are in the positive spin range. That's why there's such propulsion of space, expansion of space, due to, the summation of the momenta of all the particles in space as they act on one neighbor to the next, just collectively. That's why, again, when two black holes, like the gravitational waves from that, or when a pulsar explodes, or implodes rather, we have gravitational waves because we're at densities where neutrons just can't exist. There's such proximity with each other due to the factors of electromagnetism, because magnetic fields are involved in neutron stars very specifically. The strength of the magnetic field is proportional to the rotational force as well as the decay rate of the neutron star, right? And due to the mass and its density and the amount of speed that energy release, all that reactions that's going on, that's just due to that electromagnetism, that attraction force, right? Between particles, because these aren't even added, they're all breaking down into neutrons. It's a neutron star, it's made of neutrons, and those neutrons are just so attracted due to all the electrons that exist, due to how the amount of mass that was necessary to get the dense core, a denser core than what typical stars like the iron cores, and cores maybe of gold or of platinum in that instance. There's also still like iron, but it's so dense to a point that it would make sense that a neutron star core would be of a material like that, or even the beginning of a black hole. Which I think one of the points when I was looking it up, the center of a neutron star might be a black hole. And that there's just so much on the outside. But then it would end up beating up and then it would turn into a black hole. So maybe that there has to be a certain threshold, obviously. And there's measured thresholds. I forget what the name of it is, but this is just going through that whole idea of when that transition limit happens, there should be some way of measuring, the quark soup, because that is the in between, neutron star to quark star and then black hole. So that's that quark soup, and when it's dense enough to a point where it supersedes the quark soup. So it would have to probably do with that magnetic field energy. So depending on the density of electrons versus protons, and the protons is dependent on how dense it was to begin with. It's kind of like it has to be like exponential in some sense relative to the density, mass, and volume because of that pressure, and it has to do probably inversely with vacuum pressure. Maybe these are just ideas, at least. I'm not saying that they're right. I'm just working through the thought process. That's why it's kind of a different video because this is theoretical to an extent, but certainly when it comes to proximity due to gravity, like the proximity effect that is induced by the vacuum energy, which might lend to gravity in terms of neutrons in particular, because once we get to that point where the magnetic field is strong enough where there's enough traction that the density supersedes the density of a single neutron, the neutrons break down into protons and electrons and neutrinos. That's what we get when we have higher energy neutron stars. We get extreme amount of neutrinos coming out, just like our sun, in a sense, except even more than that because there's so much energy released. And with the release of those neutrinos, it's particles of energy. Even if it's like field energy or whatever, it's still an interaction force. It's a mass that's interacting with the space that already exists and adding into that, because they go into space and they either annihilate with their antiparticle pairs if they exist, or they're there in space and we measure them as a CMB. Like, and if there's any like other free particles that are like strong enough, or if some antiparticle particle pairs go into an electron and they create atoms in space, and then the gas clouds and the nebula from the supernova, etc., it some of it changes. There's that possibility. Again, this is where probability comes into play. But if we can understand what would dictate a neutrino's evolution or annihilation, its convergence or divergence from reality, then maybe we can figure out that quantum gravity. Maybe. But it's gonna be a big friggin' equation in regards to particle interaction, because we're gonna have to look at all the particles, like the tau neutrino, the muon, the all the fermions, mesons, etc. All of those. I mean, at least granted, in the instance of a quark star or a black hole, they're lower than neutrons. We're taking neutrons out of the equation. We're looking at least the up and down quarks. There's probably a lot of assembly, disassembly, or maybe the quarks are just there and they're making other smaller forms of mass because they can't, because it's so dense due to the electromagnetic field. And mind you, when the neutrons break down into protons and electrons, that's only adding more to the electromagnetic field. And maybe that's why black holes end up being black holes, because there's so many small particles that are so densely packed in the space that it moves. It is enough force and enough just density to move neutrinos itself out of space. Why it ripped space time, right? And everything else that would be bigger at that point. Neutrinos are smaller, but is perhaps maybe, obviously, if the density is going to infinity, it's going to be denser than a neutrino. Even though currently we don't see neutrinos or quarks or particles that small to have volumes in that sense, because we're looking at them in field equations, not what they're physically are necessarily in the quantum realm. But I think obviously there's the fact that they're not really tangible either, because if they're space, they're not interacting with us. It's almost impossible to observe a lot of these things. I mean, not almost impossible, but you know. So this is just a few of the ideas. I mean, if I get time to actually go into everything in detail with the equations, and then also see if my rate of change equation, basically, or the emergence to convergence, how things flow in the universe, the even the hold, time dilation, all that little equation, if I can get that done, modeled, and then perhaps that would be maybe the constant factor in regards to pressure density. And obviously pressure has to do with temperature and excitement, and when a quark star is that dense that it goes to a black hole, I mean, as we observe, smaller black holes, so if it's a smaller mass initially, smaller black hole, and it's hotter, we get to feel the heat. But if it's a bigger one, bigger mass, and it's colder, and it's more, I mean, it's more infinitely dense, essentially, at the singularity, because it's that's what's pushing out. It's that rush to the singularity, like I've been saying, because at that point, anything that's in the singularity is breaking down into a neutrino or photon, and is being, that's the only way that it can react due to the inward pressure, that inward vacuum pressure energy at that point, because it's so dense that it's pushing the fabric of space, and then now the fabric of space is the inward pressure coming from the outside, right? It that's probably, like I said, the inverse of vacuum energy or inverse of vacuum pressure, I believe, has to do with quantum gravity in that sense, because if the density is so big that it's pushing space is obviously going to be having an equal and opposite force on that vacuum. That's what's maintaining the black hole's density, and then also pushing the evaporation for the singularity. Because then once it gets to a neutrino or gamma ray, at that point it's small enough that it can escape through all that, as we observe. The Hawking radiation, the gamma rays, and the neutrinos and antineutrinos. They don't annihilate on the way. I'm sure internally, because it's so dense, has a higher likelihood of reacting, but there's clearly a possibility of escape for particles, specifically neutrinos. So that must have to do with something, and that would probably be the gravitational wave, because the neutrinos going out at the speed of light, or maybe even faster at that point. I don't think faster, but well, I don't know. I don't know. Because it has to obviously get into the event horizon, which I think, yeah, that is what builds up the event horizon. Anyways, that's part of the mass that's measured, and that's where we get the transition within the event horizon. So yeah, and I think the only offsetting force for that vacuum pressure, obviously, is this centrifugal force of the black hole itself, because it is a mass, even if it's like infinitely dense with almost zero volume going toward the center. But on the outside, at least, there, the rotating mass, there is a force acting against, the force of constraint from the vacuum of space itself. So maybe that's that, maybe. But I'll let you know if I get time to work on that. At least this whole idea is out there. If anyone wants to explore it, go for it. I mean, hopefully it helps. But it is a different perspective. It might sound crazy, might sound jumbled, but better than nothing. And it kind of just, it makes sense in the way that we think about, how black holes come to be. And maybe obviously we can't calculate the singularity, but maybe we can calculate leading up to the singularity, like a limit of sorts, like I've said before. And then using the whole understanding in the electromagnetism realm, we're limited in the gigavolt range, obviously, or the giga electron volt, whatever it is. We're limited because once we get to a certain point, then using electromagnetism in the quantum realm as a way of defining gravity breaks down. But I'm sure that is a force that is relative within the quantum realm up to that point, as a force that acts on other charged particles in that space. So between that and thermodynamics, because the thermodynamics lends to energy excitement, that lends to possibility of interaction, that controls what can and can't happen to an extent, especially with density, because the denser it is, the hotter it's going to be, especially at the center. So that definitely has a play. And I know that one of the articles that we went through that came out in the Scientific Journal, whatever the hell it was, that had the thermodynamics being applied to quantum, well, particles, and I think it was bosons as well and stuff like that, that might relate to a lot of other things. So there's something, but there's something that needs to get put together with what's out there, and I'm sure the answer is there. I'm just not privy enough or able to have the time to really work on all this in a meaningful way. So not yet, at least, but maybe we'll see. Anyways, until next time, this is Spark saying peace.